Greetings, and welcome, astronomy fans. This is Dr. Elena Hyde, and I am here once again with a fabulous Wednesday night York Observatory YouTube TeleTube program, the online astronomy and astrophysics program written and presented by students, faculty, alumni, and friends of York University. I am just absolutely thrilled to bring you a wonderful program on galaxies this evening. You will have three amazing hosts, Gagan, Sana, and Pelvisha, presenting all about galaxies. So make sure to tune in and ask any questions you might have in the chat or even in comments afterwards. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. We do broadcast these every Wednesday night at 7:30 p.m. local Toronto time here on York U Observatory YouTube. Now we have of course, any questions or comments allowed in chat while the broadcast is going. If you have extra things you would like to email us, please feel free to pop us an email anytime at observe@yorku.ca, or of course, follow us on Twitter or Instagram at York Observatory. All right, let's go ahead and get started.
Good evening, everyone. I'm Gagan, and I'm here today with Sana and Pelvisha from York University's Alan I. Carswell Observatory. We'll be talking all about galaxies, starting with the basics and then going into their formation and evolution, and finally, larger galactic structures. We hope you enjoy the presentation. Galaxies are massive structures, and over 200 trillion of them populate the universe, one of them being our own Milky Way. Before we go into the details about how they form, let's lay the groundwork. What are galaxies? Galaxies are gravitationally bound systems made up of stars, gas, dust, and dark matter. Most galaxies contain anywhere between tens of millions of stars to trillions of stars, with smaller galaxies dubbed dwarfs and larger ones giants. Most galaxies have a denser core region with a black hole surrounded by a less dense region, either an ellipsoid in elliptical galaxies or a disk in spiral galaxies. While they look super dense from afar, they are actually gigantic structures that are mostly made up of empty space and are thousands of light years wide. Similarly, when pictured in deep field images such as the Hubble Extreme Deep Field pictured on the left, they look small and close together. Every point of light in that image is a galaxy. In actuality, most galaxies are millions of light years apart. Our closest large galactic neighbor is the Andromeda Galaxy pictured on the right of the slide, which is 2.5 million light years away. Our own galaxy is easy to see in a dark, clear night sky. It appears as a band of bright stars and gas stretching across the sky, looking almost like a band of spilled milk, giving it its name. This region, dense with stars, is the main disk of the Milky Way. However, for hundreds of years, astronomers believed that the Milky Way was the only large structure of its kind in the universe. Some galaxies, visible with the naked eye or with early telescopes, were considered nebulae, such as the Andromeda Nebula, shown on the right. For many years, the question of whether the Milky Way was the only galaxy in the universe remained unanswered as the great debate. However, in 1924, Edwin Hubble used the period luminosity relationship of Cepheid variable stars, discovered by Henrietta Swan Leavitt, to show that Cepheid variables in the Andromeda Nebula were too far away to be part of the Milky Way and were therefore part of another galaxy. The Andromeda Nebula was therefore reclassified as the Andromeda Galaxy. Since this discovery, thousands more galaxies have been identified, imaged, and researched, with the current estimate for the total number of galaxies sitting in the trillions. Like with any field of study, being able to classify and organize subjects of research is important, and galaxies are no exception. They can be classified in a number of ways, but let's talk about the common methods. Galaxies can be classified based on their star formation rates, nucleus activity, and morphology. Morphology is the most widely used method for classifying galaxies, but star formation rates are more useful in classifying extremely distant galaxies, as their morphology can be difficult to determine. Star formation is determined through spectra, which indicate the average age of most stars in the galaxy. Galaxies with bluer spectra are considered actively star-forming, while those with redder spectra are considered non-star-forming or dead. Bluer stars are hotter and more short-lived compared to redder stars, so galaxies containing mostly blue stars must have formed them relatively recently. Another way to classify stars is based on the activity of their nucleus. Most galaxies have supermassive black holes at their centers, and galaxies whose black holes are still accreting matter are considered active galaxies with active galactic nuclei, or AGNs for short. Inactive galaxies, on the other hand, have much dimmer cores relative to their disks. When Hubble began his research on galaxies after his discovery of the Andromeda Galaxy, he also developed a classification method based on galaxy morphology and shape. Hubble divided galaxies into three main categories: elliptical, spiral, and lenticular. And galaxies that did not fit either of those three profiles are classified as irregular. While Hubble presented his morphology as a sequence, this sequence does not represent the stages of galactic evolution, as only a range of commonly found galaxy structures. Sana will be going into more depth about galactic formation and evolution in a little bit. Elliptical galaxies are denoted E, with a number describing the degree of ellipticity. These galaxies are the least structured and basically look like big clouds of stars, gas, and dust. They are usually composed of older, lower mass stars and have low star forming activities. The image in the middle is of an elliptical galaxy. Spiral galaxies are denoted S and include a subtype of barred spiral galaxies, denoted SB. All spiral galaxies have a flat disk of stars and matter, and this is where the spiral arms are located. They have a central bulge, which is a more rounded area of matter at the core of the galaxy, where the supermassive black hole is located. Surrounding the whole structure is a spherical halo of stars and globular clusters, and a much larger spherical halo of black matter. Dark matter is a theoretical form of matter that accounts for much of the mass in the universe and explains its observed structure based on existing gravitational laws, but it has not been directly observed. Barred spiral galaxies are a little different in that they have a bar structure of stars and matter around the core from which the spiral arms originate. Lenticular galaxies were part of Hubble's original classification, but they basically look like a hybrid of an elliptical and a spiral galaxy, with a disk structure but less prominent spiral arms. Galaxies that don't fit any of the aforementioned categories are classified as irregular galaxies. These galaxies don't have well-defined structures such as spiral arms or central bulges, and they're relatively small. These galaxies are usually the result of collisions, which you'll learn more about in a few minutes. An example of an irregular galaxy is shown on the top right. Now that you're all caught up with galaxies and their classifications, you might be wondering, why do we need to study galaxies? Well, researching galaxies gives astronomers a lot of insight about the structure, organization, and evolution of matter in the universe. Studying more recently formed galaxies shows us how matter interacts and aggregates in space, but studying distant galaxies is like a window to the past. Space is so vast that it takes a really long time for light to reach us from the most distant places. When we observe an object, its distance in light years essentially translates into the age of the light we are observing. When we look at our sun 8 light minutes away, we see the sun as it was 8 minutes ago, and this also applies to distant astronomical objects. The universe is about 13.7 billion years old, and our solar system has only existed for the last 4 billion of those years. The most distant galaxies we are able to observe are 13.3 billion light years away. Observing these galaxies is like using a time machine to see the universe when it was relatively new, and can provide us a lot of information about how the earliest galaxies formed and how matter behaved following the Big Bang. Comparing galaxies billions of light years away to closer ones allows us to see how organization of matter in the universe has changed over time. Studying galaxies also helps us understand more about our own galaxy, including how it formed and how it will continue to evolve in the future. Up next, Sana will take you through how galaxies are born and how they live out their lives.
Now let's talk about how galaxies form and evolve. One thing to keep in mind through this section is that galaxy formation and evolution is quite complicated, and there's still much to be learned about it. Projects like the James Webb Space Telescope, which is set to launch on October 31st, 2021, will help to answer many of these questions. Let's start with looking at the formation of disk galaxies. Disk galaxies formed early in the history of the universe out of large clouds called halos that are made up of two things: dark matter, which makes up most of its mass, and baryonic or normal matter that we interact with on a day-to-day basis. The dark matter will play an important role gravitationally, while the baryonic matter will go on to form stars. Galaxies form when this cloud begins to collapse, which is caused by clumps of matter in the cloud gravitationally attracting the gas and dark matter surrounding it. This causes the clump to grow, and after some time, it will have accreted much of the gas in the halo, forming a galaxy. But gravitational collapse is only half the story for disk galaxies. The other important factor in their formation is angular momentum, which is the ability of a system to maintain rotational movement. When these halos form, they all have a given amount of angular momentum, which, according to conservation laws, must stay the same over time. This means that the gas cloud will not be able to collapse along the plane of the disk, because if it did, angular momentum would not be conserved. This leads to the gas above and below the plane of the disk collapsing, but the collapse along its plane will be halted and a disk will form. Further features of the spiral galaxy, such as its spiral arms and a central bar, will form due to disturbances in the gravitational field along the disk, causing matter to clump together in those regions, much like how the halo began its collapse into a galaxy. How about elliptical galaxies? One possible explanation for their formation is that elliptical galaxies form the same way as spirals. However, the halos they form from did not have much angular momentum, so they were never able to form a disk. However, a much better explanation is that elliptical galaxies did not form directly from halos, but instead formed when disk galaxies interacted with each other early in cosmic history. This explanation makes sense for a variety of reasons. However, astronomers are not 100% certain this is where all elliptical galaxies came from. This is also the same process that forms irregular galaxies. So let's take a look at some of these interactions. There are many kinds of galaxy interactions, but the most prominent one in terms of elliptical galaxies is a merger, which is when two galaxies collide and then merge to form a larger one. Mergers can be separated into two distinct cases that depend on the mass of the merging galaxies. One case is a merger between a large galaxy and a smaller one, usually a dwarf galaxy. This is called a minor merger. Due to the massive difference in size and mass in minor mergers, the morphology of the larger galaxy will be largely unaffected, while the smaller galaxy will be completely destroyed. Minor mergers start with the small galaxy orbiting the larger one as a satellite galaxy, after which it will be torn apart due to tidal forces. This will cause its stars to form a stream into the larger galaxy, and eventually all its stars will have merged with the larger one. You can see the stream created by the dwarf galaxy surrounding the larger one, NGC 5970, in the image to the left of the slide. This process is currently happening between our own Milky Way galaxy and the Sagittarius dwarf galaxy, which is shown on the right of the slide. The Sagittarius dwarf is thought to be the same type of object that helped form the Milky Way. Scientists currently think that its shape might help us to determine what kind of dark matter is in the Milky Way halo. The second kind of merger is called a major merger. This is where two galaxies that are of roughly the same size collide and merge. Three examples of major mergers that are currently taking place are shown on the slide. In this case, the morphology of the two galaxies will undergo massive changes. This is because they are both about the same size, so the high velocity of the collision and the gravity from each galaxy will have a large impact on each of them. Elliptical and irregular galaxies form as a result of this process. Two spiral galaxies will collide, disturbing the stars and gas in both of them, and eventually forming either an elliptical or an irregular galaxy. This is exactly what will happen between the Milky Way and Andromeda galaxies in a few billion years. Additionally, two elliptical galaxies can undergo a major merger, and when this happens, a larger elliptical galaxy is created. One important part of galaxy evolution has to do with their central black hole. First of all, the mass of the central black hole correlates with galaxy properties, such as its brightness and the velocity of its stars in the central bulge. It is not currently clear exactly why this is happening, since the central black hole makes up a very small percentage of the overall galaxy mass. A more important factor is the activity of the associated black hole, whether or not it has an active galactic nucleus. As Gagan mentioned, not all galaxies have AGNs, but the ones that do can be massively impacted by them, as we'll see next. In short, AGNs occur at the center of the galaxy due to the supermassive black hole. They are some of the brightest objects in the universe and emit all kinds of light, from low-energy radio waves to optical light to even high-energy gamma rays. AGNs all have the same structure, however, they can have different appearances depending on what angle you observe them from. They all have a central black hole that is surrounded by an accretion disk, which is a disk of matter that is swirling around the central black hole as it falls into it. As matter in the accretion disk falls towards the black hole, it heats up due to friction and emits a lot of light. Some AGNs even have one or two jets that originate from its core and emit strongly in the radio wavelengths. AGNs often emit a large portion of light from the galaxy, and the brightest AGNs, called quasars, will even outshine their host galaxy and can be up to 1,000 times brighter. This is quite remarkable. AGNs occur on scales of just a few light years, yet they can be brighter than the entire galaxy that is filled with billions of stars. What happens to the central black holes during mergers? In minor mergers, the central black hole of the larger galaxy is unaffected, while the central black hole of the smaller one will eventually be absorbed into the larger galaxy. The case is much different in major mergers. During the merger, the two central black holes will begin to move towards each other and will eventually begin to orbit. After orbiting each other for a period of time, they will merge into one even larger black hole. Depending on the relative sizes of the black holes, this can result in the merged one being shifted from the center of the galaxy and even ejected from it completely in the most extreme circumstances. Mergers can also trigger AGNs by feeding the black hole at the core. During mergers, gas can get flung around into different areas of the galaxies and can even fall towards the galaxy core, causing more gas to fall into the black hole, making a large accretion disk and thus an AGN. Finally, one important question in extragalactic astronomy is how exactly galaxies move from star forming to non-star forming, which is a process called quenching. Stars form out of cold gas, so galaxies quench when this cold gas gets used up and there's none left available to form stars. There are many different mechanisms through which galaxies can quench, but they all have the same result. The cold gas that is required to form stars gets either removed from the galaxy or heated, so there's no more cold gas available to form stars. Quenching can be separated into two different categories. One kind is called mass quenching, which happens because of processes in the galaxy, independent of the environment. This typically involves feedback mechanisms that heat the cold gas so that it cannot collapse to form stars. One kind of feedback is through supernova explosions, which are the incredibly powerful explosions that happen when the most massive stars in the universe die. An example of the nebula left behind from a supernova is shown on the right of the slide. When a supernova explosion happens, incredibly hot gas gets ejected out into the galaxy, which heats the surrounding gas, stunting star formation. Another feedback mechanism is through AGNs, which dominate heating in larger galaxies. AGNs will heat the galaxy either mechanically by creating powerful jets and winds from the gas surrounding the black hole, or through radiation from quasars. It can also eject gas from the galaxy in the form of jets, an example of which is shown on the left of the screen. The other kind of quenching is called environmental quenching, which, just as the name suggests, depends on the environment that the galaxy is found in. Environmental quenching can happen in four main ways, and typically happens in high-density environments such as clusters that Palvisha will talk about next. The first way environmental quenching can occur is through mergers. When a major merger occurs, the gas in each of the galaxies will begin to interact, and large clouds of gas will collide. This will initially trigger a burst of star formation, but as mentioned before, this will also trigger an AGN in one or both of the central black holes. This will cause AGN feedback, just like in the case of mass quenching. When a minor merger occurs, quenching can be shut off by cannibalism, and yes, that is the technical name for the process. Here, quenching happens because as the smaller galaxy is being torn apart, its gas is also being heated, preventing further star formation. The second quenching mechanism is called harassment. Harassment happens during high-speed galactic collisions where the galaxies are moving so fast that they do not have the opportunity to merge. The galaxies will still interact with each other, and due to gravitational effects, the gas in the galaxies is heated and ejected outwards, stunting star formation. On the left of the slide, you can see the trail of gas and stars from the Tadpole galaxy after an interaction. The third quenching mechanism is called ram pressure stripping and happens because the space in between galaxies is not empty, but is filled with gas called the intracluster medium, or the ICM for short. When a galaxy is moving through the ICM at very high speeds, the ICM will act as a wind and creates a force that removes weakly held gas from the galaxy, preventing further star formation. You can see two examples of ram pressure stripping on the screen. You can see the trail of gas originating from the whole galaxy in the image on the left, and the trail of gas from the core of the galaxy on the right. The last kind of quenching is called strangulation or starvation, and again, that is the technical name. This is when a galaxy exhausts its supply of cold gas, either through star formation or through other kinds of quenching, and is unable to accrete more gas from its surroundings. With no more cold gas, it will not be able to make any more stars. Exactly what mechanism is responsible for quenching galaxies depends on various factors, such as whether or not the galaxy is in a cluster. Stay tuned to learn more about clusters from Palvisha.
Thank you, Sana. So now that we have an understanding of what a galaxy is and how each individual galaxy can be classified, I'm going to talk about their different physical distributions. So to summarize what a galaxy is essentially a collection of stars, dust, and other celestial objects that are gravitationally bound. However, galaxies themselves are also gravitationally bound to each other in what are called galaxy groups or clusters. Galaxy clusters are composed of around 50 or less galaxies, but can also exist as incredibly small groups of galaxies with around 4 to 5 galaxies within a group. These small groups can be classified into 3 different types: compact galaxy groups, fossil galaxy groups, or protogroups. Each of these different types are certain stages of the evolution of these small groups. So what a compact galaxy group is a group consisting of a small number of galaxies with around 4 to 5 members that are isolated from other galaxy groups. An example of a compact galaxy group is Stephan's quintet, which, as its name suggests, has 5 galaxies. These then evolve to become fossil galaxy groups. A fossil galaxy group is the merge of all galaxies within a compact galaxy cluster. What is left behind is an elliptical galaxy resulting from the merge, and surrounding it, a cloud of gas emitting in the X-ray wavelength. These are isolated from other galaxies and galaxy groups, and due to the nature of their formation, they can teach us a lot about the formation and evolution of galaxies within a small group. The other classification is a protogroup. So these are basically the beginnings of a compact group. They're a smaller form of a galaxy cluster called a protocluster, and are galaxy groups that are in formation. So it basically means that there are galaxies involved in the process of forming a group. These tend to be composed of very young galaxies called protogalaxies. Our Milky Way is also part of a group of galaxies. It belongs to what is called a local group, so it's not a small group of galaxies. The local group actually consists of more than 50 galaxies, of which the Andromeda Galaxy and Triangulum galaxies are also a part of. These in the Milky Way are the largest of the group, and the rest of the galaxies are dwarf galaxies that are satellites of the 3. The group has a diameter of around 10 million light years. So, for reference, a light year is the distance light travels in a year. Light travels 200,000 meters per second, and there are around 31,536,000 seconds in a year. So, as you can imagine, 10 million light years is incredibly, incredibly large. It's also important to note that there is no galaxy at the center of the group. It is easy to assume that the Milky Way would be at the center, but that is not true. There is no central galaxy, but the cluster does have a gravitational center partway between the Andromeda Galaxy and the Milky Way. The local group lies on the edge of a larger distribution called a supercluster, specifically the Virgo supercluster. Adjacent to the edge of the Virgo supercluster is the local void, a region of space that is, as its name suggests, completely void of galaxies. An interesting fact about the local void is that while all other galaxies in the local group are moving away from the local void, there is one dubbed the Lost in Space Galaxy, or NGC 6503 as per its new general catalog name, that is in fact moving towards the local void. A supercluster such as the Virgo supercluster, also called a local supercluster, is a collection of galaxy groups that are gravitationally bound to each other. So they are essentially a large group of galaxy groups. The Virgo supercluster consists of the Virgo cluster, the local group, and around 100 more galaxy groups or clusters. It is around 110 million light years across, so 10 times the size of the local group, and contains about 100 billion times the mass of our own galaxy. At the very center of the supercluster is the Virgo cluster, which is located 65 million light years away from us, the largest member of the Virgo supercluster and the supercluster's namesake. Interestingly, the local group isn't just a part of the local or Virgo supercluster, it's also a part of what's called the local sheet, which is a region of space where the members of the local group and other galaxies it encompasses share a peculiar velocity. The region of space above the local sheet, adjacent to the local group as mentioned before, is the local void. The local sheet is inclined at 8 degrees to the rest of the supercluster and consists of the local group and also what is known as the Council of Giants. The Council of Giants is a ring of about 3.75 megaparsecs in diameter, composed of 12 large galaxies surrounding the local group. The local sheet itself is around 7 megaparsecs or 23 million light years in diameter, but only 0.46 megaparsecs or 1.5 million light years thick. So it's incredibly flat, practically a sheet or a pancake. Learning about the local sheet and the local group's connection can help us better understand the evolution of the local group and the galaxies within it. Sounds like the structures we've covered so far have gotten pretty large in scale, but it doesn't stop here. The Virgo supercluster, of which the local group and the Milky Way are a part of, is part of an even larger supercluster called the Laniakea supercluster. Consisting of the Virgo supercluster, the Hydra Centaurus supercluster, Pavo Indus supercluster, and Southern supercluster, the Laniakea supercluster contains a whopping 100,000 galaxies scattered across a region with a diameter of 160 megaparsecs or 520 million light years. The image shown is a model of density with bright lines showing where the galaxies should be. The red dot indicates the location of the Milky Way. The gravitational center of the Laniakea supercluster is called the Great Attractor. It is to this which all galaxies move towards, hence its name. The Great Attractor was first discovered in the 1970s when maps of the cosmic microwave background were created. The cosmic microwave background is residual radiation from the time and creation of the universe, where electrons and photons combined to form hydrogen and released photons in the process. The cosmic microwave background can be detected in every direction in the universe. The fluctuations in the CMB are what led to the structure we see today. Anyways, back to its connection with the Great Attractor. It was back when maps of the CMB were created that astronomers discovered that the CMB was hotter on one side than the other, implying that the Milky Way was moving through space. What does it turn out the Milky Way was moving towards? The Great Attractor. To end this off, I want to talk a bit about a very interesting structure called the cosmic web. Turns out, superclusters like Laniakea can be found in larger structures or walls and filaments of galaxies like the Great Wall or the Sloan Great Wall. Unlike the previous structure studied, the components of these filaments, like the Sloan Great Wall, are not gravitationally bound. These filaments intersect at nodes where the distribution of galaxies is the most dense, with large spaces of emptiness between called voids. These voids take up around 95% of space. This network of filaments and voids composes a much larger structure called the cosmic web. The structure of the cosmic web that we see is due to the existence of dark matter and the fluctuations in the CMB. The structure of the cosmic web can be depicted as being sponge-like in appearance. Zooming out of the cosmic web, however, this network disappears. Everything becomes one homogeneous chunk of galaxies. This point of homogeneity is called the end of greatness, and is also one of the underlying principles of the universe as we know it. We can finally, at the largest scales, see signs that the universe is homogeneous and isotropic as predicted by general relativity. Well, everyone, you have been listening to the Allen I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Gillian, Sana, and myself, Helvetia. Make sure to leave any comments in the comments section of the video. You can always connect with us on Twitter with the handle @York Observatory, and check out our website for show notes, content updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.
Wonderful show, and thanks to everyone who is tuning in. Just a little reminder, we will be online in chat for about the next 20 to 30 minutes answering any questions you might have about tonight's show.